Welcome to NASA's Digital Learning Network Summer of Innovation Special Webcast Series, featuring the following topics every Tuesday and Thursday through August 19th. Mother Earth, Father Sky, life science, the universe, aeronautics, rocketry, and robotics. If you would like to submit questions to our presenters during this time, please feel free to email those questions to nasalearn@gmail.com. That's nasalearn@gmail.com. I'm your host, Karen Long, speaking to you from NASA Langley Research Center here in Hampton, Virginia. But our guests today come to us from California at Ames Research Center, DLN coordinator Greg Pitzer and his special guest. Greg, how are you today?
We're doing wonderful out here in sunny California. We're out here at the Ames Research Center in the San Francisco Bay Area. And I'm privileged here to talk to you guys a little bit about the Kepler mission, where we're actually going to be looking, coincidentally, for suns. Sunny California, we're going to be looking for sun-sized stars that have Earth-sized planets orbiting around them. Now, I know a little bit about the mission, but fortunately, I have a special guest here who's going to tell you every single little detail you might want to know and give you some neat little activities you can do in your classroom as well. So, with no further ado, let me introduce you to Edna Devore, Kepler Mission.
Good morning. It's so nice to be here today, and I'm delighted that you're all interested in NASA and in the programs that we're engaged with. As an educator and as a scientist, I'm intrigued by questions that have to do with how do we learn about other places in the universe? And so the program I like to think about that we're presenting today is Chasing Shadows. This is NASA's Kepler mission. And I'm going to step back in here and show you a few pictures of where we exist in the universe. Behind me is an image from the Hubble Space Telescope. This is the Hubble Space Telescope Deep Field image. And everything except the single star that's right over my shoulder is another galaxy. Each of those galaxies has someplace between 100 billion and 500 billion suns. Now, the galaxy we live in looks like this, and our sun, you can see, is pointed out there. We're out in the outskirts, maybe you could call it the suburbs of the Milky Way galaxy, in a relatively quiet place with a lot of other stars that are about the same age and size as the sun. And those are the stars that we're interested in looking at for the Kepler mission. Here's an image of our space telescope. This is the spacecraft that we've named Kepler. It's pointed out looking up there in the corner at a star that has a planet in orbit. The Kepler spacecraft orbits the sun, not the Earth, as many other satellites do. We named it for Johannes Kepler. He was an astronomer who lived about 400 years ago, and he was really the first person to figure out how planets orbit the sun. And he came up with Kepler's laws that explain that we can see planets in orbit about their stars on ellipses, and we can figure out how far they are from their stars by how long it takes them to go around. And this is true in our solar system, and it's true in every other solar system that we've found so far. The Kepler spacecraft was designed and built by people at Ames Research Center, Jet Propulsion Labs, Ball Aerospace, and several other companies worked on it. Here we see it under construction on the left. It's about 15 feet tall and about 9 feet in diameter. That's about the dimensions of a big-sized ice cream truck that you might buy a lollipop from in the summertime. On the right, you see the spacecraft mounted on top of the rocket at Kennedy, ready for launch. We launched in 2009. It was a night launch, and I think that the next images we'll see here will show the launch. It's a short video of the spacecraft launching at night. It was really a terrifically exciting mission to watch launch.
7, 6,
Greg, I think we
5,
need to get the sound cut in here. We're good?
3,
okay.
2, engine start, 1, 0, and liftoff of the Delta II rocket with Kepler on a search for planets in some way like our own.
Burning our engine chamber pressures are building. Groundlit solid motors are building at chamber pressure. Increasing at this time. pressure's looking good. 1 second into the flight. Recovering from the initial launch transients. Passing 34 seconds. Mach 1. Vehicle's now going supersonic. Motor chamber pressure is beginning to trail off as we're passing 45 seconds. Engine chamber pressure, good steady state value. Symmetrical burn on the groundlet solids. Coming up 55 seconds. Standing by for burnout. Burning out of the solids. And for separation. See separation. And we have ignition of the airlit solid motors. Airlit solid motors building in chamber pressure.
When we watched that from the ground at launch, it was a very exciting time because in about 2 minutes' time, we watched 25 years worth of dreaming and imagining, designing and engineering go up on a rocket and had to wait for almost 25 minutes before we could really recontact our spacecraft and find out that everything was fine. And it was, and it has been ever since then. So for me, it was very exciting to be able to be at the launch and watch the spacecraft take off. If you ever have an opportunity to do that, I recommend it. So what is Kepler looking for? We're looking to ask the question, are there other worlds like the Earth in orbit around distant stars? And what Kepler is going to be able to tell us is if there are other worlds the size of the Earth. And I'll spend a good deal of the rest of the time explaining exactly how we do that. When we think about planets, and here you can see the planets of our solar system arrayed out. This is a scale model where the planets are the right size. They're not the right distance apart, but they are the right size. And we group planets into big groups. There's the gas giants, otherwise known as Jovian planets, because they're like Jupiter. There are the Earth-sized worlds like ours. Venus, Earth, Mars, and even Mercury can be thought of as an Earth-sized world. And then there's all the little teeny planets that are now called dwarf planets. And that includes Pluto and several others. As time goes on, we're finding more and more small objects that are like Pluto. Here's an array of those. And a good deal of this research is being done by people at California Institute of Technology. A guy named Brown there is finding a lot of these using very large telescopes to sort out and find very faint objects. But these are not really planet-like. You can see that even some of these are not quite round. So we're interested in planets the size of the Earth. And in comparison to their stars, as you can see in this image, they're really quite tiny. If you look up here carefully, you'll see a very small dot that represents the Earth inside that solar flare. Good thing we don't live that close to the sun. It would be a very toasty place to live. But it gives you a sense of the comparison of the size of those two objects. The sun is a middle-sized star. It's not too hot. It's not too cold. It's about 4.5 billion years old. And we're looking with Kepler at stars like the sun and smaller. Stars that are a great deal bigger than the sun, more massive, are much hotter. They live shorter lives. And we're more interested in finding stars that would host planets where it might be a good place to live. So what do we mean about a good place to live? This image really is showing you what the environment of 3 different stars might be. And if we look at hotter stars than the sun, you'll see that the green area around the star is farther away if we look up here at the top. If we look in the middle, this represents a sun-like star. The green area is a little closer in, and if we look at the bottom here, the green area is even closer. Think of that green area as being a comfortable zone to live in if you're a planet that has life upon it. For the Kepler mission, we're defining that green area as being the habitable zone, a place that you can inhabit, and where you would find liquid water on the surface of the planet. So the bigger, the brighter, the hotter the star, the farther out the habitable zone, the longer the year is for the planets. Stars like the Sun, a habitable planet might have an orbit much like our own, about 1 year long. For cooler stars, the habitable zone could be much closer in, and so a comfortable place to live might only take 7 or 8 months to orbit its star. So when we start doing this kind of research, we really have to look pretty closely to discover planets that are going to be habitable around different kinds and different sizes of stars. We have to know a lot about the stars to do that. And the method we use is called the transit method. Now, lots of people think that transit means a bus, or transit means a survey instrument that helps us figure out property boundaries. The transit method in astronomy is entirely different. What the transit method in astronomy is it's looking for the little tiny dip in light as a planet goes in front of its star. And if you look at this image of our sun, you see Venus right up here in transit a few years ago. That was a photograph that was taken as Venus was passing between the Earth and the sun, and you could see its shadows. So we think of transits as chasing shadows. And what I'd like to do now is switch over to a couple of demonstrations to give you a little better idea of how transits work. So we'll go over to a table here and I'll show you what I mean. Here we have a light bulb, and this is sort of just a standard light bulb, and it represents a star. And I've got a nice wooden bead that's sort of Jupiter-sized. Jupiter's about 1/10 the diameter of the sun, so this is a Jupiter-sized bead. And as the planet orbits the sun, you can see that it's crossing in front of the lamp. And for teachers in the audience, these are simply beads that you can acquire at a craft store. Nothing special. I use black thread because it's harder to spot the thread that way. But this is Jupiter. And so from the surface of the Earth, astronomers find Jupiter-sized planets in transit because they block out 1 to 2% of the light from the star that they're transiting. What I'd like to do, though, is to see what happens as we go to smaller planets. Jupiter is by far the largest planet in our solar system. If you put all the other planets together, they would not be as big as Jupiter. So here's a planet that perhaps is the size of, let's say Saturn. So now here comes Saturn by. It would move more slowly, of course, but it's hard to make a slow loop with a string. And so you can still see this one fairly easily. This is a good-sized planet. It would probably block out something less than 1% of the light of its star. If we keep going down to smaller sizes, here's perhaps a planet the size of Neptune or Uranus. And you see it's starting to get a little more challenging for us to pick out how much light would be diminished as the planet went by. Now let's try an Earth-sized planet. These have all been pretty big planets. These were all Jovian or gaseous planets that we looked at earlier in the pictures. Here's my Earth-sized planet. See if you can spot it coming by. It's pretty small because the Earth is only about 1/100th the diameter of the sun, and so it's hard to see the transit of a very small planet unless you're close to the star. And in our case, we're very far from the star, and so all we see really is a point of light, and we don't actually see the object going across the face of the star. We only observe the light from the star and look for the amount that it diminishes. So Greg's going to change our view over here to a different model, and I'll go over to the computer and set us up to take a look at a different way to understand transits. What we have here is a model of a solar system. You might want to tip that camera up just a little bit. The lamp, of course, represents the star. And here's a planet. And over here, This is an optical sensor. Think of this as being our Kepler satellite, and in fact, we'll make it look like the Kepler satellite pointed at the star. And as our planet orbits the sun, you can see it go by. Well, with the Kepler mission, we look for these kind of transits, these crossings of the planet across the star continuously. And that data is sent down to Earth. In our case, it's being sent through a wire into the computer to where we can see a chart or a graph. And what I'm going to do is run the model and have the computer record the light level from the lamp as the planet crosses in front of the lamp. And you can see that each time the planet crosses by, we get a dip in the light. And that's what the transit method looks for in trying to discover planets. Now, our solar system has 8 planets plus all the dwarf planets. It has 8 pretty good-sized planets. Let's see what happens if we had a system here that had 2 planets. I've now just started another one up here, so we'll just look at it. So we have 2 planets going around the star. You'll notice they go at different speeds and that they're different sizes. The inner planet goes more quickly, just like they do in our solar system, the outer planet more slowly. And so now let's record that data and see what happens as these 2 planets transit the star. So the small one is still making its sort of steady little march. But when the big one comes by, we see it as a larger dip, and we see it spaced more broadly. And it's so from the frequency of the transits, that's how often they occur, we can get the year length for the planet. And from the depth of the dip, we can figure out the size of the planet. And so Kepler's looking for planets around stars like the sun that take about a year. We want these dips to be a year apart and are about the size of the Earth. And that's a very tiny dip that we can show you a little bit later. So this is a different way to model what Kepler does, but what the Kepler scientists get for all our efforts is they get light curves. And you see a good model of one right now here up on the screen. And again, the difference between this dip and this one gives you the time it takes for the planet to go around the star, and the depth of the dip, the percentage of light that's blocked, can be used to calculate the size of the planet in comparison to its star. And so we can find out if we found a Jupiter planet, or if we found an Earth-sized planet, or if we found a Neptune-sized planet. We can find out what the size of the planet is. We can't tell from the Kepler data whether or not there's water on the surface. We can only infer or deduce that there could be water on the planet if it's far enough from its sun to be comfortable and water could be liquid there. Remember the habitable zone? That's what we're looking for. Okay, so we're going to switch back to some images here. We're using transits. We just modeled those. And if we zoomed away from that star until it was a fine point of light, you obviously couldn't see the little tiny dot of the transit. So all we can look for one more time are those dips. So where are we looking? Okay, here's the sun, and we're looking in space over here in the Milky Way in the direction of the Orion Spur. We're looking along an arm of the galaxy that's about the same distance from the center that we are, and has stars that are pretty similar to the star that we orbit, the sun. This is our camera. Think of it as a giant light meter. Every one of those nice shiny blue squares with a little line down the middle is 2 chips. It's about 2 inches square for each set. There's 42 of them. And every time they take a snapshot of the sky, it's a 96 megapixel image. The camera in your cell phone might be a megapixel, 1 megapixel, or 2 megapixels, not real high resolution. You might have a really good digital camera that will take images that are up to 10 to 15 megapixels for a single image. This camera takes a picture of the sky every 6 seconds, 96 megapixels. And out of that, we select a small number to keep and record that represent the stars that we've taken from the whole field. So where is Kepler looking? What we've done here is we've imposed the outline of our camera on the sky to show you how much of the sky we're seeing at once. This is a big piece of the sky, and for those of you who are astronomy buffs, the red triangle up there represents the summer triangle between Deneb, Vega, and Altair, 3 of the brightest stars in the sky. You can see that summer triangle high overhead at this time of the year. And so you can find out where Kepler's looking by looking almost straight over your head at a nice comfortable time in the evening. You'll see we're near the Milky Way. It comes down through, across diagonally through our image here. But we're not right on the Milky Way because there'd be so many stars it would be confusing. As it is, we have about 4.5 to 5 million stars in this entire field. And I'm just going to back out here so you can take a good look at the field. If you want to see this really close up, please visit our website. You can dive in and look individually at the images on each of those chips. Trust me, there's about 4.5 to 5 million stars sprinkled into this snapshot of the sky. Of those, we've picked out a small number, about 150,000 stars that are similar to the sun, to watch and to look for transits. We don't know when the transits will occur. We don't know if we'll see the transits because you have to be lined up to have that planet cross in front of the star. And so we only expect to see transits on about 1% of that 150,000 stars. And so far, that's how the numbers have played out in our observations. So what have we found? Well, here's the first 5 planets that were discovered by Kepler. You can see the light curve shape. Remember those dips they make when they go in front of their stars? Each of those transits would take several hours. And these were announced in the first part of 2010. And they're all planets that are close to being the size of Jupiter. The larger the dip, the larger the planet. Only the one right there is smaller. And they all have very short orbits because these are the first ones we found. When we want to look for Earth-sized planets around stars like our sun, and they come around once, then we have to wait about another year to see them come around again, and we wait another year to see them pass by the 3rd time to confirm that we have an Earth-sized planet. We're only about 15, 16 months into the mission, and so we still have quite a ways to go to be able to say whether or not we have found a planet that looks like the Earth. These are the ones that have been announced so far, and in the next couple of weeks, keep your ears tuned because there will be new papers being published on the Kepler mission announcing new discoveries. This is data that's used to back up our discoveries. This was taken at the Keck Observatory in Hawaii. We think we found a Jupiter-sized planet. They go to their observatory. They observe it in an entirely different way. And these curves tell us that, yes, indeed, the host star is wobbling around because it's being tugged on by this big, close-in orbiting planet. It's called the radial velocity method. And those confirm it in 2 ways that we've actually found planets. So how big are these planets? I call these the jelly bean planets. We really don't know what they look like. Remember, we're not taking photographs of planets. We're actually only looking at the diminishment in light that they cause when they cross in front of their stars. They cause a little dip when they transit. So we painted them to look like, I don't know, jelly beans or funny-looking pool table balls. And you'll notice that 4 of them are larger than Jupiter and 1 of them is smaller, still bigger than the Earth, but smaller. And these are all very hot planets. If you think of the vertical line, let me go over here. If you think of this vertical line here as like a thermometer, our Kepler planets are the ones that are up here at the top, and they're extraordinarily hot. It could rain molten rock, lava, or gold, or even iron on these planets because these are all at temperatures that would melt iron or gold or lava. Down here, where we see the Earth, is a more temperate kind of temperature, and this is what we're looking for. So far, this is what we've been able to announce from just the first 45 days of data. And as time goes on, more planets will be found that are farther from their stars and present a more comfortable place to live. So we do this because we seek other worlds to understand our place in the universe. That's really the goal, the big goal of this kind of research. And I'm very pleased and excited about it. Kepler will continue to make these observations for at least the next 3 years. We may extend the mission beyond that. That's NASA's choice. But on board, it has enough materials, consumables, gases to reorient the spacecraft and so on to last for up to about 10 years. And we've been up for about a year and a half. I'd be delighted to direct you to the Kepler website where you can learn a lot more about this mission. And if you have any particular questions that you want to ask me, my email address is edevore@seti.org. I'd be happy to hear from you. And I'd be delighted now to entertain any questions that have come in from our viewers.
All righty.
All right, Greg, thanks.
Thank you very much. I know that was a wonderful talk there. I know I always learn something new each time I hear it. So it's great to hear the presentation again. I think we'll probably have some questions here as well. We'll definitely encourage you to send questions via email to us. We'll be taking questions for the next few minutes here. One thing that's always exciting to me is we often hear about, hear presentations about missions that are going to take place, or missions that, finish, or, the shuttle comes back. We found out what happened up in space. But it's kind of neat. This is actually going on right now. Yeah.
Absolutely. The Kepler mission is in space now. It's drifting slowly away from the Earth. Its orbit takes about a dozen days longer around the sun than we do, so it's a little bit slower. And it will continue to just depart from us. And why did we do that instead of having it orbit the Earth? Because we wanted to always point in the same direction in space. And if it did that orbiting the Earth would get in the way half the time. And so we put the spacecraft out into space so it can always point at that nice patch of sky up there in the summer triangle.
Now imagine these orbits, take a little while. You may see an orbit come around once, every couple of years. If it's an Earth size, or the distance from a planet is the same as Earth is from our sun, it's once a year. So how long can the Kepler mission stay up in space, assuming we have funding and the mission is approved?
Well, the Kepler spacecraft itself will never come back to Earth, so it'll always be in space. But how long can we do science with it?
Right.
We can do science for at least 3.5 years. As we continue to make more discoveries and we go back to NASA headquarters and ask for ongoing support, we could run as long as 10 years. I think it'll be something between 3.5 and 10 years, personally, because in that period of time we should have enough data to be able to describe well what kinds of solar systems there are in our galaxy, whether or not Earths are common or they're rare.
Excellent, excellent. And what's the follow-up? So we say we find several, potential planets out there that look like they might be, a similar distance away from Earth. What do we do next with that?
Well, when we find these potential planets out there in around distant stars, other kinds of telescopes can be used to follow up and find out whether or not these objects might have an atmosphere, whether they might or might not have water on their surface. And initially that kind of follow-up work will be done from the ground with, I call it the big mirrors, the big glass, like at Keck Observatory or Palomar or the binocular telescope down in Arizona. There's multiple, the telescope in the Canary Islands. All of these telescopes are working on Kepler follow-up work now, and they'll continue to do that. There are 2 big projects, one European and one American, to build a telescope that's 30 meters in diameter.
Wow.
30 meters in diameter is almost 100 feet across. Now, this is not going to be one piece of glass that's 100 feet across. It'll be multiple pieces of glass that all act to focus together. And those will be able to do from the ground some amazing kinds of work to sniff out whether or not these planets we discover have atmospheres or water. NASA is going to be launching the James Webb Space Telescope in, I believe, about 3 or 4 years, perhaps sooner. And that will also be an excellent instrument to be able to follow up and learn more about these planets. But I think the most exciting thing about Kepler is it's going to tell us whether or not the planet that we live on is a rare phenomena in the universe, that, it's maybe one of a kind, or whether there's lots of other planets like the Earth around other stars. And I think that's a tremendous step forward in our understanding of who we are and where we are.
I think I heard someone quote me earlier, we're very unique, just like everyone else, possibly.
Oh, yeah, well, there's that too.
Well, we'll find out. Maybe we'll find out how unique we truly are here at Earth, whether there are other Earth-sized planets out there.
I think we will find out something about ourselves by exploring in space. And I really think, for me, at least personally, that's the motive for understanding astronomy and for doing more space exploration, is that we learn about ourselves by understanding the natural world. And I get excited about that just as a human being. You know, separate from my job and my, things that I get to do that are fun, I'm just excited about it as a human being to really be a part of this exploration of the universe. I really enjoy it.
Well, talking about excitement, because I know you have a background in education, and I think there's a bunch of activities and other information related to the Kepler mission that teachers can use in their classroom. I was wondering, maybe you could talk a little bit about those activities and other material that teachers can use.
Yes, I'd be happy to do that. And I don't know if we can go to the website and highlight some of these. This is our website at kepler.nasa.gov. And if you have the opportunity to go there and you visit the Education tab or the Education section of the website, there are a whole raft of activities for students of many ages. Everything from a coloring sheet that might be suitable for a kindergartner who just wants to make their own picture of this spacecraft, to activities that have taken the light curves we're collecting with the spacecraft and have adapted those into inquiry lessons for the classroom. All of our activities include national standards, so you'll understand what part of the National Science Education Standards you're meeting by conducting these in your classroom. There's a full set of instructions for how to build an orrery out of Legos if you're a Lego person. Those are great fun to make. And the initial demonstration I did with a bead and the light bulb to explain what a transit is well explained on the website. We also have a rotating star map. Astronomers call those planispheres, but it's a star wheel. And it has a date and a time, and you can cut it out and put it together and rotate it to your date and time and see what's up in the sky. And marked on that star wheel, Greg, are all of the stars that we now know that have planets around them. They're not necessarily planets that Kepler has discovered, but they're stars that you can see without a telescope that are known to have planets. For example, one of the very bright stars in the sky is called Pollux. It's part of the constellation Gemini, typically visible easily in the fall and winter, and it has a planet around it. And you can walk outside and you can point at a nice bright star in the sky and say, that one's got a planet around it. Not just our sun, but that star right there. And so on our star wheel, we kind of edit it up every so often and add the new stars where new planets are being found, because we know about, I didn't look it up this morning, I'm sorry. Last time I looked, we know about more than 450 planets around other stars.
Wow.
In our nearby neighborhood.
Wow.
This is just in our neighborhood of the galaxy. And only 5 of those planets so far have been discovered by Kepler. But I expect a waterfall of new planets to come from the Kepler mission, because we have a lot of very interesting data that will be published over the next several months. And people will see that there's lots and lots of planets in the universe.
Excellent, excellent. Well, I know students are going to be kind of our next generation of explorers here, and I think this is a great way for them to kind of get started, kind of seeing what planets are out there, where might be focusing some of our efforts here in the future. So, again, I encourage teachers to go to that website. There's lots of great materials on the kepler.nasa.gov. Lots of also PowerPoints from the researchers and presentations and some of the raw data. You can also get right there some of the photographs. So I encourage you to go there if you want to share this information with your students in your classroom. So with that, I think I want to thank you very much for your presentation, for all the information you've shared with us. I always enjoy watching the orrery go around and seeing how you can collect data, very similar to the Kepler mission there. And hopefully teachers here have also learned a few things about this and a couple activities they can use in their classroom. So with that, let me toss it back to Karen and Langley.
Thank you, Greg and Edna, for sharing with us today. And thank all of you for joining our webcast. Join us on Tuesday, August 17th and Thursday, August 19th for our presentations from Marshall Space Flight Center. Stay with us for Edline News to learn more about what NASA education is doing for students and teachers. Have a great afternoon, everyone.